You're still there. You know it's bedtime, right? Hmm? You're gonna make me carry you upstairs, are you? There you are. Yes, you are. Hmm? Well, hello everyone. A few people have asked me to do this update, and I have wanted to, but life gets in the way, and you know, I have to make time to do things like this because this isn't my full-time job. But I will now be building this engine, and it will be finished. I won't be building it over one day. The point of this series was to talk about everything involved in doing this build, since the information's kind of lost to the way forums have died and so forth over the years. Everything that I discuss will end up going up on my website in a tech article, so I may not necessarily go over part numbers and things here specifically, but they will be a matching article where it's easier to look up part numbers and specifications and so forth going along with this. One of the reasons I struggled getting this done is because I'm not a professional at this. It's just me and my video editor, who's just a friend. He just does this for fun. He's not usually present during the filming. Anyway, I'm just going to do it off the cuff. Each video in this series or chapter, depends how it gets done at the end, is just going to be talking about the specific components and the details of what's involved. So on the first video, I just kind of went over the components briefly. Now it's time to go for a deep dive. We'll begin with the block, which you can see is all taped up. The reason it's all taped up is because partly because I painted it, and partly because I have cleaned it thoroughly after having it machined. Now, if we pull off the tape and reveal the insides, I do have it upside down on purpose because we'll be putting in the crank today, so we'll be starting from this side. But you should be able to quite clearly see the bores, and we'll have a better look when I roll it over for the bores on the other side. But you can see the bore. So this block has been overbored. I think it's 84 or 85 millimeters is a standard bore. It has now been bored out to 87 millimeters. That's the nominal value. It isn't actually 87 millimeters. I think it's like 86.8 or something like that. And that is to fit these S54 pistons. So the exact values will be on the website. I'll also give some guidance on tolerances, though you should generally work with your machinist or your engine builder, depends how you're going down it, and take their advice, generally speaking. The other way you can do it is you can actually go and look up the tolerances for the S54 and get the tolerances from BMW and say that's what we're going to do, which I also have and I will be putting on the website. So for parts of this, I've gone with some recommendations from the machinist. So the bores here are actually just as the machinist recommended for the clearances, but the rings, I have gone and gapped them to BMW specification, and same with the bearing clearances. And we'll get into those details a bit later on. But that's the overview for getting the block ready. Is it just needs to be bored correctly and clearanced correctly for your pistons. The pistons that I'm using are the S54 pistons, which have been decked. Again, I'll get into these in more detail when I get to that chapter. Just one other little detail. When choosing your block, the M44 block is the better choice because of the oil squirters, which the M42 doesn't have. I've now installed those, and I thought I'd just get a little bit of a close-up so people can see what they are. But yeah, these are a hollow bolt, and the oil squirters squirt pressurized oil up onto the back of the pistons. And this is one of the reasons why the M44 has a larger oil pump than the M42. It's because it actually has more oil leaks to atmosphere, I guess, is a way to describe it, because it needs to supply more oil. But yeah, if you're choosing a block, if you do have the choice, pick an M44 block. Now we're on to the main course for this part of the video, which is our crank. There's actually quite a lot to discuss with this crank, and so one of the fun things about filming by yourself is trying to work out filming angles. I've tried to give it so that you're not looking at my back the whole time while I'm working on my bench, which makes things more awkward for me, but it also does make it a little awkward to get a clear shot. So I'm trying to prevent some dust getting into this, but I also want to use this as my my bench. So so this is the crank I'm going to be using. There are a few cranks you can use, and there's also the stock cranks, and I don't have my M44 crank, so we'll put some pictures up on there, but we'll start with the M42 crank.
Going straight to the top, we don't wait, we don't stop.
Alright, it's now time to talk about crankshafts. The crankshaft you're looking at here is the M47 crankshaft, but we're going to start by talking about the M42, which is the first generation crankshaft. It has the smallest bore and stroke, the M42. The stroke is 81 millimeters, if I remember correctly. It is a cast steel crankshaft. I know everything you read says that they're forged, but every single one I have seen has been cast. It's possible that in the early days when the engine was built for a small run of homologation cars, I believe, that they may have used a forged crankshaft then, but I've never seen anything from BMW that discusses that the crankshaft is forged, and I've never seen a forged M42 crankshaft. So I don't think it's likely that any of them are. Hello, Future Hayden here. I just wanted to say that as soon as I finished filming that section, one of my friends sent me a photo of his M42 crankshaft, which was very, very clearly forged. So, are they all forged? Are most of them forged? Are some of them forged? I don't know. But they definitely can be found forged, which is good to know. Especially if you want to build a turbo, because that means you could, say, de-stroke and decompress an M44 a little bit, turn up the boost, and basically just see what happens until you break a piston, because that crankshaft will definitely be strong enough to see where it goes. Have fun building your engines. That said, there are still benefits to the M42 crankshaft. The first is that it's fully counterweighted, and the M47, which you're looking at here, is also fully counterweighted. What that means is that every single piston has the two counterweights. On the M44, where they were trying to make it more efficient, they actually reduced the weight of the crankshaft quite significantly by making it a half counterweighted crankshaft. And they also put the timing wheel on the crankshaft so that it would be part of the balancing of the assembly. But the downside for the M44 and the upside for the M42 is that because of that counterweighting, it is a more intrinsically balanced crankshaft, which means you can rev it a bit higher before it starts to act like a skipping rope. In machine balancing, you refer to anything you're balancing as a rotor. When these long rotors hit a resonant mode, they actually become a flexible rotor, and they start to behave like a skipping rope, and they'll bend like that. So having full counterweights means you can rev a bit higher before you start getting to this issue. Generally speaking, it pushes that resonant mode further down the line. That's not correct. If you're an engineer in the comments who specializes in this, please don't get mad at me. I'm just trying to make it palatable. But we will talk more about balancing because it's actually really important. So that's the M42 crank. Decent at revving, probably not forged, and small stroke. Then we get to the M44 crankshaft. I briefly said that it's not fully counterweighted, which does make it more efficient because it weighs a lot less, especially a lot less than this forged steel crankshaft. But it just won't rev very high. One of the issues is that when you start getting into high RPM, there's a chance that you'll actually blow that timing wheel apart. I know people who have built engines whose guidance I'm actually following for this. They break M44 crankshafts once you get to really high horsepower or high RPM, and that's naturally aspirated. So you will get a little bit more life out of the smaller M42. But the real reason you're here is this crankshaft. You want the 88mm stroke, not the 90mm if you're going for high horsepower. And the main reason is that these ones are forged. You can quite clearly see the forged markings on this crankshaft. If I just get the right angle there, See how fat that joint is? And that's because the big die has come down and stamped that crankshaft. So the 90mm ones aren't forged. The other issue is the length of this nose here. On the 90mm, the nose is short. So if you're trying to find one of these on eBay or window shopping somewhere, that's the main thing you need to look for, is the length of this. There are a number of modifications you'll need to do to this crankshaft to make it suitable. The first one is to turn down this outer diameter. Now, I think it's only about 1mm that it needs to be turned down to the factory, but it is a nominal diameter of 31.5mm. Now, the reality is that this fitting here is not going to be 31.5mm. Actually, it's what's called a slip fit. I can't remember the exact tolerance call out. What it means is that when you put something over this, it should be able to move freely with a little bit of encouragement. You shouldn't need press tools. So you should actually take your lower crank timing gear with you and get them to fit it to that gear. So you can see I can get this on, but if I don't get it exactly the right angle, it'll actually sort of catch and be difficult to remove. So I don't want to put that on because that is a slip fit, not a press fit. And you can see here on my older timing gear that I can quite freely get that over, but there should basically be no play. So take your old crank with you, they will measure that up and get that to be the correct nominal diameter, and they'll have the correct kind of micrometers to measure that diameter, and you want them to match that to your existing crank. There will be some tolerance, but I don't have that from BMW. So you do want to either take the gear with you or the existing crank, and you want that matched to the same tolerance that the original part was, not just the same diameter. Because if you go and get something like this, and that gives you, like I said, it'll give me 36, whatever it was, 31.63. There you go, 31.63. That's not right. It's going to be 31.5 or 31.6. It's just not accurate enough to read the kind of value you need for the tolerances that this needs to be machined to. So it needs to be read with a micrometer, and the easiest way to do that is if you just take the old part with you, or you take the new part with you and say this needs to be a slip fit. Not a press fit, not a fit, a slip fit. So that's the first thing. So that outer diameter needs to be turned down. If you get one of the 90mm ones, the cranks where they're not forged and they've got the shorter nose, you actually have to weld on a new nose and then turn it down, and that just sucks. The second thing that you need to do is to get a new keyway placed. So you can see here I've got a full-length keyway put into the nose, but that's trivial for a good machine shop. They'll be able to do that for you easily, and they should have the Woodruff keys on hand. They basically just cut a little channel in and then they press that in place, which is exactly what I needed. So that's almost the end of it. So that's the end of the modifications, but for this crank you actually do need a correct crank bolt. Your M44 or M42 crank bolt will not work. I will have the BMW part number for this on the website, but that is a different crank bolt for this crank. Hello, it's Future Hayden again. One thing I forgot to mention with this crankshaft is you also need to get a custom washer manufactured, which is easy as finding someone with a lathe to turn some metal for you. I have some drawings for it, which I will flash up on the screen, but they'll also be on the website, so if you want to just take those drawings to someone and say, make me this fancy washer, they can do that for you. The reason you need the fancy washer is if you have a look at those pictures, there's a weird little lip on it, and that lip is used to center the bolt in the crank pulley. Why they did it that way and no one else does it that way, I don't know, but it's as simple as just making another washer that will center in that pulley for you. Yeah, back to the video. There is a fourth crank you can get, and it's worth noting that anything I discuss on the in these videos, I will either be able to help you purchase or be able to sell to you through my website. Even if it's not listed, you can send me an email and I'll be able to help you out. But you can get a billet crankshaft. I do make them. I generally don't have them in stock because my business is too small. I don't really keep a lot of things in stock. Most of the stuff is made to order, but I've got a manufacturing partner who will make you a billet crankshaft. So that's kind of it for your crank options. Yeah.
When do we want it? Tell me, when do we want it?
Now, that's kind of what you need to know. There is one other thing which has come up a couple of times when I've been discussing with people, and that's balancing your crankshafts. I'm just going to straight away say don't. If this is what you're doing, don't do it. If you really want to lighten your crankshaft to try and make up for the extra weight of this compared to, say, an M44 or M42 crank, then you have to get it balanced, but I would actually really strongly recommend against it. And before you just go, oh no, this is something you're supposed to do, I do actually know a little bit about balancing. Actually, I know enough to know that I don't know enough about balancing, and that's kind of why I know you shouldn't do it, because I know more than people who are saying that they do know about balancing, and that really distresses me. So we're going to go on a little bit of a rant about machine balancing on cranks. Now, if we rotate this around, you can see that this has been balanced from the factory. This would have been done probably through an automated machine, probably through a shank machine, and this will be well within the G16 tolerance that they set for crankshafts. I don't know exactly what they would have been, but it probably would have been G16, but they would have been able to target it more. But most importantly, whoever set that machine up would have actually known about balancing far more than I would, and definitely more than your local shop who has a busted out machine. And the small changes that we're making, just changing the diameter on this ever so slightly and the extra mass from this keyway, are not going to have any realistic effect on this internally balanced crankshaft. So don't do it. Need a bit more convincing? Well, I was actually installing a balancing machine for a drive shaft shop recently, and I took a little bit of footage to show you what a balancing machine should look like. So we'll cut to that. So just for a bit of perspective, this is a balancing machine I'm installing. This is a shank machine. This is at a drive shop, drive shaft shop. So this is a brand new bit of kit. That's the control unit. And these spindles here are for doing drive shafts. So if I just pick up the cover for a second, you can see we've got a flange on here and a spindle, and that's where you connect it. And down here you've got some sensors. But over here, this is what we're working on today. We're setting up for the calibration. And this is what a balancing machine should look like. So just to give you a bit of perspective, these are some springs. That's what all these cutouts are for. They're a calibrated spring. And we have a sensor over here. And while this is spinning, those springs will vibrate at a known frequency based on the imbalance, and it all goes back to the computer, which does its black magic. And that's how you can work out the imbalance. Now, the problem with a lot of shops that do crankshafts is that they'll often have like a milling machine sort of just here, just above the crankshaft, and they'll use that to remove material, and it puts force down into these springs and they deform, and then all of a sudden the machine actually isn't measuring anything useful anymore. There's a whole lot of other issues, but I just thought I'd make this quick clip to insert just so you can see the condition of a working balancing machine. And if you have a look at the balancing machines in most automotive shops in Australia especially, I don't know what they're like in other countries, but in Australia, most of those machines have never been calibrated, they've never been serviced, the springs will be bent, you know, sometimes they'll go and tap you know, fittings and things into the springs, which throws the calibration off, and they've got no calibration records, and it's just a disaster. So yeah, if you do have a factory balanced crankshaft, you're just better off leaving it alone. Now, having a look at that machine, when you walk into any shop that's going to be doing balancing, especially for crankshafts, the first question you should just ask them is, when was the last time that the machine was calibrated? They will almost always say they have no idea, they don't do it, or they calibrate it every time they run a crankshaft on it. Now, if they say that, that would be a very good indication that the machine doesn't work, because they'll probably be doing something along the lines of a rotor-specific calibration, where they've gone and cut out some weights that they know the mass of, and then they go to put them on. I've seen a couple of balancing machines for crankshafts, and there's all kinds of issues. If you look up videos of them online, and it's really hard for me to sort of talk about this because I don't really want to go and get someone's video where they're talking about how they do balancing in their workshop and then just pick it apart. That's just kind of rude. You know, they'll do things like drill on the balancing machine. Now, the balancing machine has these calibrated springs. If you're applying pressure with the drill, you're now deforming those springs, which means that your balancing machine doesn't work. They often use very old measuring units, which don't give, clear or easy to interpret results. It's actually a really complex field doing balancing. So unless you absolutely have to rebalance your crankshaft, you shouldn't. On that topic, if by any chance there is someone who runs an engine shop who either really knows what they're doing or is willing to go on camera and discuss that they might not know what they're doing, I would really love to actually talk with someone about like what's involved in balancing, if that's something you guys are interested in. It's just, it's definitely the sort of thing that if you go and get this balanced, you'll get a number, but it will probably be worse than the balance that it has in the first place. To give you some perspective on the issue, when we installed that machine, we actually did a little bit of training on a drive shaft, and I took a photo of it. We did it, went through the method, and the operators were like, well, we've always done it this way. So they went and got us a balanced drive shaft. We put it on the machine, and I kid you not, we removed the exact amount of weight they put on that drive shaft to balance it in order to actually get it within the specified tolerance. And they were just completely unaware. And it's like that at every shop I've ever been to in Australia when it comes to drive shafts, even NADA accredited labs, they don't, their machines aren't maintained properly, or they're not calibrated properly. There's only a very small number of places I've seen where they approach balancing correctly. It's a complicated engineering topic, and most places don't approach it that way. So, yeah, little rant over. Just leave it. It's better off like this. Anyway, I think now I should put this in. I think I should install it because that's kind of what I'm here to do. So let's crack on with that. All right, bearings. The way that BMW do bearings is they have you can see their standard size. When you go and look them up online, they'll actually come with standard, and then they have different colors. I can't remember what they are. There's a couple ways you can do it. You can go and measure this, and then measure your bores on your mains, and then work out exactly which bearing you can get. Or you can just buy a standard bearing, because unless there's a reason for you to think that your bearings are going to be need to be oversized, say if you've had these polished, which I have, then you can get the next size up. But generally speaking, it's just easier to get a set of bearings and then put them in, measure them with plastic gauge, and if they're wrong, just get the next set of bearings, which is the approach I took. It's a little bit more expensive, sure, but then how much does it cost to go and buy all of the gauges that you need to do those measurements anyway? So the approach I've taken is put it together and find out. Now, I've actually already sort of put this together once and then pulled it apart for filming, and then did it again because I was trying to find the best way to present all this for you guys. And that's why we're doing the long form waffle, just kind of saying random crap and hoping that someone watches this. So let's crack on, shall we? I'm using the factory clearances, which I was very kindly provided. And that's what I am working from, which I'll actually bring up as I'm doing all this again so I can say the right numbers. So the factory spec for these bearings is a 0.02 millimeters to 0.046. Now, depending on who you ask, they will actually do more. Most engine shops will actually suggest that you run quite large clearances. I think from their perspective, it's probably safer. Also, if you're building a race engine and you know that you're always going to be in the high RPM, you might actually be a little bit more concerned about the flow of the oil. For me, even though I'm building a more strung out engine, I'm targeting keeping that in spec. So yeah, time to assemble all this. Now, I know depending on who you ask, you shouldn't put any oil on your mains, but there's this, I guess, idea that they'll slip. But I'm actually more concerned with scratching, bending, or catching the bearing. And honestly, once there's oil in the engine under pressure, there's going to be oil getting everywhere, so I don't really buy that. Now, this is my first time building an engine, so, you know, if you don't want to listen to me, that's fine. If you know better than me, please leave a comment and I will genuinely take it on board. So if you see me about to do something disastrous, yeah, please let me know. So these bearings, I've opened them up a while ago and I'm just cleaning them all up to make sure there's no dust from them having been sat around, and just wiping them clean, and then everything will go together again like magic. Happy days. Now, your mains, they're all numbered. I took photos of mine to know which main goes where, which I am now going to find and open up again. Now, I don't know if your numbering will be the same as mine, but it might be or it might not be. Time to put some assembly lube in and sit the crank. At this point, you will need new main cap bolts, which I have, but we're not using those yet because I am going to go through and check all the clearances on these using Plastigauge. Now, there's a million videos showing you how to do this step. I'm just another one of those people who's going to do it. Even though I did it before, I'm going to do it again just for peace of mind and just so we can discuss the clearances on this specific build, which is the main reason I think anyone would be watching this, is they're more interested in exactly what goes into doing this exact build. So let's do that. So these bolts are 17 millimeter, and I'm just going to get them all started and then check all the tightening torques. So I'm just using the old ones because these bolts are, in theory, they're stretch bolts. I actually don't think they are. I think these are all going to be reusable, the grade 10.9, but I'm actually curious. I've got some tools that I can use to measure the torque when we do that, you know, the tightening thing. But the reason I'm reusing these is so that I don't have to stretch my new bolts to check all the clearances. So let's just get them all started. Now, don't stress, I'm not using these to actually tighten it up. I just don't want to spend all day doing it. So let's just get them going. Now, I've heard that you should sort of check that these will rotate freely as you tighten each one. You will find that it will actually kind of seize each time you do it. So, yeah, you kind of got to work your way down gently. So as I went down, you could actually see that these would rock back and forth as they seat. But once they're all correct, you can see how freely that moves. There's effectively little to no resistance on that. That's easy to move by hand, which is how it should be. Anyway, time to pull up the specs for this. So this is a dial torque wrench. It just lets me see the actual value of torque I'm applying. So 20 Newton meters, 20 Newton meters, 20, 20, 20, 20, 20, 20, 20, and unsurprisingly 20. That's still rotating nice and smooth, so that's all seated well. Now I have to apply 50 degrees. So I just did a little experiment with the tightening torque. I used a gauge for angle, and I used a dial gauge torque wrench, which you can use to actually measure the tightening torque that you're applying. And it comes up with about 65 Newton meters. Now these are an M10 grade 10.9 bolt, which means that the specified tightening torque, which I just checked, is 72 to 82 Newton meters. So working with any error in my gauge, I got a couple that were probably 65 to 75 Newton meters. That was the actual range that I measured. I genuinely have no idea why they specify that as an angle, because it's clearly achieving the tightening torque that's specified for these bolts. I'm still going to do it that way because that's the way that BMW says to do it. The only reasonable reason I could think to do it is it might have less error than the error in a torque wrench. I don't know. If someone knows the answer to that, please let me know. But I find it really interesting that the specified angle lines up with the specified torque for a bolt like this. Hello again, Future Hayden visiting from the future. And this time I'm visiting to tell you I know the answer to my own question. The reason that you use an angle when doing tightening on a critical bolt is that you can actually increase the clamping force as you move into the plastic deformation range, right up until the point that the bolt will begin to yield and it'll go backwards. I might pinch a graphic from Wikipedia and sort of stick it up here somewhere. Now, the other part, which is of my question, was why are these bolts lining up with the tightening torque of that grade of bolt? The answer is it's just a total coincidence. Normally that's not the case. It just so happens to be that with whatever pressures BMW was expecting with these, they didn't need to tighten them to a certain point, and the recommended torque that they gave just so happens to be the actual recommended torque that those bolts would see. There is, however, a benefit from using that angle regardless of setting the tightening torque. And that is that most of the torque that you're applying is overcoming friction. Now, if you don't correctly oil the threads as you're tightening these things up, that friction will be more. And rather than risk going to a specific tightening torque and the actual applied clamping force being too low, what they do is they go, well, go to this torque and then just really reef it around and that'll do. So those tightening angles are literally just, let's just make sure. And they go so far that they know they're in the plastic range so that those bolts are no good most of the time. Just by coincidence, in this case, you could probably just tighten these bolts to 65, 70 Newton meters and call it a day if they're oiled properly, since there's not a large angle being applied and they're quite a high grade bolt. But yeah, that's all it is, just a coincidence. But the reason they use that angle is to make sure that you account for assembly error, because in this case, you're not actually concerned about the friction of the bolt coming undone. You're concerned about the amount of clamping force so that when an explosion happens and that main bearing moves down from that extra force, it moves the most minimal imperceptible amount so as not to damage your engine. So yeah, I learned something, maybe you learned something, maybe you didn't, maybe you're smarter than me, maybe you already knew that, or I don't know, maybe you just don't care. But I found out and I'm telling you anyway. Back to the video. Anyway, what I will be doing now that I'm going to be measuring the clearances, I'm just going to use that as a shortcut. I'm not going to bother doing the angle again because I have to undo all these and measure each of them individually. I'm just going to tighten them back up to 65 Newton meters, or rather 70 Newton meters, and just do that because that will be a lot quicker. But when I actually put in my new bolts, I will do it properly. So let's find out what the clearances are on these bearings. Alright, 20, 20, 65, 65. All right, let's have a look underneath again. A little bit more than 0.064, smidge less than 0.05. Alright, so I've now gone and replaced all the old main bolts with new ones, which, here you go, part number. So I will put that in the on the article on the website when I finally get around to writing it, but there it is for you. So that can go in the bin, if I can get it in the bin. And yeah, so that's installation of the crank. So you can see that this M47 is just straight on a drop in. You can see I've gone witness marked all of the bolts, but I think that'll be a good first episode. And yeah, so I'm going to start filming my second episode, which will be installing the pistons, which is also quite lengthy because I've got all the piston rings and other fun stuff to talk my way through. So a quick aside about the clearances on those bearings. The factory specifications for the bearings are 0.02 millimeters to 0.046 millimeters of clearance, which, you know, I was showing before I was checking. Now, most of my bearings are actually 0.05 millimeters and I think one of them was 0.064, which is actually out of spec. So you might be wondering why I ended up tightening it all down, and that's because the guy who I know races these builds, he actually runs them with 2 thou to 3 thou clearance, which is from 0.050 to 0.076 millimeters. Basically my engine is clearanced at the low end of a race engine or the high end of the BMW spec. Because the compression ratio is going from 10 to 1 to 12 to 1, I actually think it's going from to 12.5 to 1, having a little bit better oil flow, plus the larger oil pump that's on the M44 compared to the M42, I don't see it being an issue, and it will generate more heat, so that oil will be slightly thinner anyway. So plus, with the hotter cams, I will be revving this engine out a little bit further for every gear change than you would normally, so it will have more oil flow than general. Now, however you build your engines, I would take the advice of whoever you're using as an engine builder. But if you're going to do it this way, I would probably use the upper end of the factory clearance as a reasonable guide and go from there. There should be a fairly decent amount of tolerance regardless, even if you're running it at the lower end. But generally speaking, adding more oil is less of an issue than your engine seizing or spinning a bearing. So anyway, that's why I sealed it all up and on to the next bit. But before the episode ends, I just want to say that I miss my cat. He would often sit down with me when I'm working. He's been in a few of my videos, but I lost him a little while ago, unexpectedly. I have a new kitten now, but I think I'll this episode will be dedicated to the cat who normally hangs out with me while I'm working.
Liquid gold cheese watercolor.
Sit down again, dear. Hanging out with me.
A brush stroke
Coming out
of
here,
deep
staring at the rain.
indigo.
Remember being sad. I can't do anything.
Shifting from sea foam to cyan glow. Liquid gold cheese watercolor, blurring all the lines, tinted with a kiss of summer, caught between the sea and the sky. Honey yellow heart dying folds, flickering, fading, overflow. Liquid gold cheese watercolor, blurring all the lines. She's tinted with a kiss of summer, caught between the sea and the sky. Daylight, she's a fleeting beauty, blurring all the lines. Liquid gold cheese watercolor, running to the horizon line. I brush stroke of deep indigo, shifting from sea foam to cyan glow. Liquid gold cheese water.